Okay, so the first thing I need to say is remember that the first lab exam is next week in lab. Okay, so lab exam 1 is next week in lab. It should only take about half an hour, and then that's all we're doing in lab. And remember that to get ready for these, you want to go back to your notes and just review how to answer questions like we've done in the labs. Okay, it's just going to be questions very similar to those. And if you can't make it to your lab, but you can make it to the other one, feel free. You don't have to tell me ahead of time. You can just show up to whichever one works. Anybody have any questions about the lab test coming up? Yes.
So it's just gonna be like a paper test as well.
Paper, correct. Yep. And it's going to be stuff like find. I mean, just like the questions in all the labs. So there'll be a question that's like, on this position versus time graph, where's this object moving in the negative direction? Where is it slowing down? And yes.
How many questions are you gonna
I think it's usually between 10 and 15 because they're usually short questions. But like I said, people finish. It certainly won't take you 2 hours. Any other questions about it? Okay. As far as the exams I just gave back, the scores were overall pretty good. I'd be happy to talk to any of you if you want to talk about your tests specifically. I'd be happy to go through any problems if you want to see how to do it. I'm not going to do it right now because I want to get to some new stuff. But I'd be happy to do it in office hours, over email. So just get in touch with me if you have questions. Also, on D2L, everything is updated right now. It doesn't have your weekly assignment in yet, obviously, because I think that's not even quite due yet. But on D2L, the grades should always tell you your updated grade. And so you can get sort of a good sense of where you're at. Remember, the grading scale is going to be probably pretty close to 90, 80, 70, 60. So that should give you an idea of what kind of grade you're at right now. One thing I always say, people, ask me all the time, can you tell me where I'm at with my grade right now? And, my best guess at where you're at with your grade right now is take your total overall percentage, so let's say you're at 85% in the class, and multiply it by your percentage in the daily assignments. So let's say that's 0.9. Okay, so this is your overall percentage. This is your daily assignment percentage. Let me multiply that. So if you multiply that out, this comes out to be about 0.765, equals about 76.5%. And the reason that I say this is a good way to think about it is what you know for future exams comes from how diligently you do those daily assignments. If you're not doing those problems, trying to figure them out, little by little, your scores are going to go down over the exams. Okay, if you're doing all the daily assignments, then that's great. If you're missing some of them, it's going to take its toll on your future exam scores. Okay, so I said feel free to contact me if you want to talk about your test. Feel free to contact me too if you want to talk about your grade overall or study approaches, what you think you could do to improve your score. One thing about the exam scores is remember that your final exam score can replace one earlier one. So even if you got a 2% on this exam, which I don't think I've ever given a 2%, but if you got a 2%, it doesn't have to come in your grade in the least. If you do well on the next the next two regular exams and then do well on the final exam, this one you just took is totally gone. It's really just a matter about getting your study habits right and getting stuff right going forward, you know. Okay, that's all about that. So the next thing we're going to talk about, we're done talking about 1D kinematics of particles, and now we're going to talk about 2D kinematics of particles. And so the thing that's different here is 2D now means that objects can move in a full plane instead of just moving along a line. The other two things still mean the same thing. Kinematics means basically the relationships between position, velocity, acceleration, and time. So talking about describing motion, but not dealing with the causes of the motion. And then particles are a mathematical treatment of an object. Let's just say this is where you treat an object as having no length dimensions. So it just exists at the center of mass. So we're doing the stuff we were doing before, but now we're moving from stuff along a line to stuff in a plane. One thing to remember is in 2D, we're never going to draw position versus time graphs. So any position versus time graph, remind yourself that that is representing a motion along a line. Okay, in 2D, we'll never see P versus T graphs. Okay, so like when, if you see a position versus time graph like this, and it asks you, okay, what kind of motion does this represent? A lot of people look at this and say like, oh, well, that could be like going up the ramp of a roller coaster and then going down the other side. But remember that if you have a position versus time graph, this is just motion along a line, okay? And so the way to interpret this is it's going one direction here in the positive direction, it's going in the negative direction here. So this is actually a thing that starts out in whatever is the positive direction, slows down, stops, and then starts speeding up back the way that it came, okay? So I keep trying to bring this up, and I'm gonna keep trying to bring it up, but remember, there's a big difference between whether you're looking at the path that an object follows in space or whether you're looking at a position versus time graph of a one-dimensional motion. And if you think it's one and it's the other one, everything you think about it is kind of nonsense. You interpret them very differently. Okay. Okay, so let's think back about 1D for a second. So in 1D, position, velocity, and acceleration have both magnitudes and directions. The magnitude is the absolute value. And the direction is the sign of the number. We saw that, I guess, most clearly with velocity. We'd say, okay, the absolute value of the velocity is the speed. That means something that we're used to. And the sign tells you, is it moving in the positive or negative direction? I want you to notice, though, and this is something that we did in our lab last week. So notice that we could have represented the direction with an arrow in 1D. Okay, so for example, let's say that we have an object that's moving along this surface, and let's say that the velocity is this way and the acceleration is this way. And let me say we'll call this positive and this negative. Okay. Representing these two things with arrows, we could say, okay, the acceleration is positive, the velocity is negative, and these two things together mean it's moving in the negative direction and it's slowing down. Okay, so those arrows give the same information as the signs. Okay. In 1D, though, we could represent directions with plus and minus, with the signs. Just because there are only two directions in 1D motion. So 1D motion only has two directions. When we switch to motion in a plane, so in 2D, there are a lot more than two dimensions, two directions that you can go. There's infinitely many directions. And so obviously we can't assign a plus minus sign to infinitely many directions. So we need a new way. And that is vectors. And so we're going to start out talking about 2D motion by just talking about the math of vectors. And we talked about some aspects of it in lab. We're going to, in class, do sort of more of a nuts and bolts kind of description of how to use this stuff, a little less intuition about what it means. So position, velocity, and acceleration are all vectors in 2D. And whenever a variable is a vector, we're going to show that by drawing an arrow over the top of it. So the position vector will represent like this, the velocity vector like this, and the acceleration vector like this. Time doesn't change when we go to 2 dimensions. So it still means the same thing as it did in 1D. It's just the elapsed time that shows up on your stopwatch, okay? We're always going to think of vectors as arrows. And vectors always have 2 properties. And those are magnitude and direction. You know, I said up at the start that in 1D, position, velocity, and acceleration had magnitude and direction. So they still have those same properties now. It's just we have to represent the direction differently. The magnitude we're going to think of as the length of the arrow. And the direction is the direction the arrow is pointing. And so if this is your vector, we're going to call this the head of the vector. And this is the tail of the vector. And the length of that arrow gives us the magnitude, like we can measure that with a ruler or whatever, and the direction that it's pointing to the like lower left is the direction of this vector. So in lab, we talked about how to add vectors and multiply them by numbers, and we didn't think really about what the components of vectors are. But in class, for calculations, we're pretty much always going to come up with the components of a vector. So to do math with vectors, we'll express them as components. And this is the meaning of components. So if you have a coordinate system with your x-axis this way and your y-axis this way. And let's say that this is your vector, okay? We're going to break it up into two components. First, we're going to have a vector that's parallel to the x-axis. And we'll call this the x component. And then we'll have one that goes parallel to the y-axis. And that's the y component. These are perpendicular to each other. And notice that by the rules of vector addition that we talked about in lab last week, if you add the x component and the y component together, it gives you the total vector. So you can think of like you're adding these two things to get the total vector. The most important fact about vector components for understanding this stuff, so always keep this in mind. The most important fact about vector components is if you put the tail of the vector at the origin then the vector's components are the coordinates of the head. Okay, so let me show you how this works. Oh, one thing I want to say too, so remember that vectors only have two properties, only magnitude and direction. So there's no part of a vector that cares where it's located. Okay, so you can always take a vector and move it around to different spots on the coordinate system, and it doesn't have any effect on the vector. The only way you change a vector is changing its direction or its magnitude. So let's say that we have this coordinate system. So these are the x and y axes. And let's say that we have this vector like this when we put the tail at the origin. Okay. And I'm going to draw out some units so we know 1, 2, 3, 4, 5. And then on this one, 1, 2, 3, 4, 5, 6. Okay. And so what are the components of this vector? Well, since if we put the tail at the origin, the coordinates of the head are -5, +6. So the x component is -5 and the y component is +6. And there's a few ways that people write these depending on like what kind of math you're going to do with this information. So there are multiple ways to write components. One common one is -5 times this I, that's a thing that points in the x direction, plus 6 times j, which is a thing that points in the y direction. So that's a notation that you see in physics all the time. I'm going to use a different one, but it means the same thing as this. So I'm going to use the notation x component goes on top, y component goes underneath, and square brackets do it like that. So you can think of it as it's very similar to the coordinate notation. So in the coordinate notation, you put your x coordinate first and your y coordinate second. Here you put your x coordinate on top and your y coordinate below. Okay. One thing I want you to notice about this relationship between the coordinates of the head and the components of the vector are, so from the relationship between the head coordinates and the vector components, you can always see immediately what the signs of the components should be. You can always see immediately what the signs of the components should be. Okay, so let's see this in some examples. So the question is, for each of these vectors I'm going to write up here, what are the signs of the components? So the first one is this. The second one is this. The third one is this. And the fourth one is this. Okay, so the first one, I'm going to draw a coordinate system. And then I'm going to put the tail of this vector without changing its direction. I'm going to put the tail of this vector at the origin. So let's say that's the vector. Okay, and now instead of trying to think of this as components, we've reduced this question to figuring out what the signs are of the coordinates of that point. Okay, so is the x coordinate of the head positive or negative?
Negative.
Negative, yep. And the y coordinate, is it positive or negative? Positive, yep. And another way you could think of this is the x component is the top one, the y component is the bottom one. So we can't eyeball what the numbers are, but we can we can tell what the signs are, and that's really useful when you're sanity checking your answers. You can look at that and say like, now that doesn't make any sense or whatever, you know, and then it helps you find your mistakes. Okay, B. So again, we're thinking about the coordinates of the head. So is the x coordinate positive or negative?
Positive.
Yep, x is positive. Is y positive or negative?
Negative.
Negative. And so we know the components are like that. Now we have two that go along the axis. So for the first one, it goes this way, straight along the axis. That's such an ugly vector. So the x coordinate, that's the coordinate of the head. Is that positive or negative?
Negative.
Negative. And the y coordinate, is it positive, negative, or zero, I guess in this case?
Zero.
Zero, yep. And then for the last one, it's like that. So the x coordinate, is it positive, negative, or zero? Zero. And the y coordinate, positive, negative, or zero? Positive. Yep. You can also do this in the other direction. So let's say, I'm just going to do one of these, but let's say we have a vector. Let's say we want to sketch the vector -5, let's make it +5, 0. How would we do that? Well, again, I mean, you can draw out the coordinate system or just visualize it. But you're just going to plot that point. So 1, 2, 3, 4, 5. So this is the point 5, 0. Then that's the head of the vector, and the tail is at the origin. So this is the vector 5, 0. Okay, and remember that it doesn't have any preferred location or anything, so you can move that wherever you want. It just looks like that. It's that long and in that direction. Anybody have any questions so far? Okay, so if you don't remember anything else, remember the relationship between the coordinates of the head and the components of the vector, okay? Okay, so now if you're given a vector as a magnitude and an angle from some reference line, one way that always works to find the components, so I'm going to do an example as I go here. So let's say that the vector we want is this. And let's say that we're told that it makes a 20-degree angle with the vertical. And we're told that it has a magnitude or a length of 10. Then the first step is find the counterclockwise angle from the positive x-axis to the vector. And I'm going to call that angle theta. And then the components of the vector are the length of the vector times the cosine of the angle for the x component, and the length of the vector times the sine of the angle for the y component. So for this example here above, let's think about what that told us. So if this is our coordinate system, and we're told that this vector makes a 20-degree angle with the vertical, so this angle is 20 degrees, okay? Then the angle that we want for this formula goes from the positive x-axis to the vector. So the angle that we really want is this. Okay? Well, notice that it's 90 degrees to go from the x-axis to the y-axis. So you can basically think of this as going 90 counterclockwise and then backtracking 20. So this angle theta in this case is 70 degrees. Okay? And so that means that the components of this vector are 10 times the cosine of 70 degrees, 10 times the sine of 70 degrees, and if you just punch that into your calculator. Oh, by the way, in this class, always your calculator should be in degrees, okay? So come talk to me if you're not sure how to change the mode for your angles, but we're always going to use our trigonometric functions in degrees. So this comes out to be 3.42 for x and 6.43. That is not right. This should be 9.40 for y. Okay? And that works with positives and negatives and whatever. So let's do another one where, let's say, we have our vector makes an angle of 10 degrees with this horizontal. And let's say the length of this vector is 2. What are the components? And I'm going to do this in 2 different coordinate systems this time. Usually, you know, the coordinate system that we're going to use most often is the one that you're the most familiar with x going to the right and y pointing up. Okay? But we're going to use other coordinate systems too in physics. So let's do one where the x-axis is pointing up and the y-axis is pointing this way. And then let's do another one, a last one. That's like this, where the x-axis is tilted at 10 degrees from the horizontal. So this angle is 10 degrees. And in every case, the way you're going to do it is you're just going to go from the positive x-axis of whatever coordinate system you're using to the vector. Okay, so for the first one, here's our coordinate system, and our vector is this, where this angle is 10 degrees. Okay, so what's the counterclockwise angle? If you start at the positive x-axis and go to the vector, what's that angle theta? So you go, start at the positive x-axis, go 90 degrees and you're here. Another 90, now you're at 180 and you're here. Go 10 more degrees than that, so 190 degrees, okay? So this is 2, hold on a sec. Okay, so this is 2 times the cosine of 190 degrees. And then 2 times the sine of 190 degrees. And that is, well, first, before you plug this in, let's think about the signs that we should have, the plus minus signs for this. So you can see that the coordinates of the head are going to have a negative, it's going to be a negative x coordinate and a negative y coordinate, okay? So if we don't get 2 negative coordinates, something went wrong. And we get 1.97. Does that sound, is that right? Negative? Anybody have a calculator? Is that right? And then the second one, what's this? That would be 348, negative 0.348. Is that right?
I got 0.247.
0.247 for 2 times the sine of 190.
I got 0.347.
Oh, okay. I think that's just round off error that I had there. Okay, so in this coordinate system, those are the components of the vector. Okay, now let's do B. So this time, our positive x-axis is that way, our positive y-axis is this way. So now we've rotated the coordinate system. Here's where it's easy to get like sort of mixed up. You're like, okay, we're kind of rotating everything. So where do I rotate that vector? The key thing to remember is that vector is defined as the direction it is. You don't move the vector. We just put the tail at the origin. Okay, and now the angle that we want goes from this positive x-axis, this new positive x-axis, to the vector. Okay, so what's the angle this time? So this time you go just 90 degrees counterclockwise to get from here to there, plus another 10. So the angle is 100. So we'll go 2 times the cosine of 100, 2 times the sine of 100. And again, you can think of what the coordinates at this point are in this coordinate system. You have a negative x and a positive y based on the way the coordinate system is oriented. Okay, so that's what we expect the components to come out. Negative x, positive y. And this comes out to be negative 0.347, positive 1.970. Any questions about that? Okay, now the last one. We have this coordinate system that's at kind of an angle. And because of the angle that this is at, the vector just goes straight along the negative x-axis. Okay. And so what's the counterclockwise angle from the positive x-axis to this? 180, yep. And so you can do this as 2 times the cosine of 180, 2 times the sine of 180. Or you can also just say it's straight along the x-axis, a distance, the negative x-axis, a distance of 2. And so this is just going to be negative 2 for x, 0 for y. Either way, it comes out the same, okay? But whenever they're on any of these 4 coordinate axes, you should just be able to look at that and say, well, is it in the positive or negative direction? And then that's the end of it, you know? So this comes out to be negative 2, 0. Anybody have any questions about that? Okay, let me write a couple up here and give you a chance to do these. So let's say our vector has a length of, say, 10 and makes an angle of 40 degrees with the horizontal. And we want to calculate the components of the vector. And the coordinate systems will use the usual one, and then one with the x-axis down and the y-axis to the right. And then third, let's do one where this angle here is 40 degrees. Okay, so take a few minutes and see if you can calculate these. Feel free to talk to each other or ask me questions or anything. This is just a chance to kind of solidify this stuff in your head. And I'll go through it after I give you a little time. All right, so on the first one, the coordinate system is like this. And this angle is 40 degrees. The angle we want is counterclockwise all the way from the positive x to here. And so that's, you can think of that as falling 40 degrees short of 360 degrees. So that's 320. So 10 times cosine of 320, 10 times sine of 320. You also, by the way, you can go clockwise as long as you count the angle as negative. So we could also start at the positive x-axis and just go 40 degrees clockwise. And so that's 10 times the cosine of negative 40, 10 times the sine of negative 40. And you get 7.666 negative 6.43. Any questions about that one? Okay, the second one has the positive x-axis pointing down. And you don't rotate the vector, so this angle is 40 degrees. And so now the angle we want goes from the positive x here to the vector. You know that the angle we want here plus 40 have to equal 90. And so that angle theta is 50 in this case. And so you have 10 times the cosine of 50, 10 times the sine of 50. And you get positive 6.43, positive 7.66. Any questions on that one? And then the last one, so this one's rotated at a funny angle. We're told, okay, so the coordinate system is like this. The x-axis is this way. The y-axis is this way. And we're told, I drew this pretty badly, really, but we're told that this angle is 40 degrees. And that means that the vector goes straight along this line. And so now you can see that the vector just goes along the negative y direction. So it's just going to be 0 for x, negative 10 for y. You also could calculate it as 10 times the cosine and sine of 270, or negative 90. But it gives you the same thing no matter what of those you use, 0, negative 10. Any questions? Okay. So now that we've talked about what these components are, how you come up with the components, now you're going to see why we put vectors into components. You saw what it, what it means to add two vectors in lab. You saw what it means to multiply a vector by a number. When you have the components, these calculations get super easy. So now this is the vector math we're going to use for components. Vector math using components. Okay, so the first thing we're going to do is add two vectors. And remember in lab, adding two vectors meant that you make each vector like a leg of a trip. And you follow the first one, then follow the second one, and then the sum is the shortcut. Okay. If you're adding two vectors and you know the components for both of them, so let's say the first one is AB and you're adding it to the component CD. The sum of those vectors is A plus C for the X component, B plus D for the Y component. And it's not immediately obvious that that's the same thing that we were doing in lab, but if you did the approach that we talked about in lab really carefully with a protractor and a ruler and everything, you would see that this is the same. Okay. So for example, if you have 5, -5, and you're adding it to 1, 6, the sum is 6, the 5 plus 1, and then 1 for the Y. The second thing that we're going to want to do is multiply a vector by a number. So if we're multiplying C times a vector AB, what you get is an X component that's just C times A and a Y component that's just C times B. So like if you're multiplying -6 times the vector -3, +4, the vector you get out of this is 18, -24. And that works exactly the same way as multiplying the magnitude by 6 and then switching the head and the tail like we did in lab. Okay. And then the last thing you might sometimes have to do is to calculate the magnitude of a vector when you know the components. So if your vector, let's call it U, is AB, then we denote the magnitude as like an absolute value of that vector. And so the magnitude of this vector is the square root of A squared plus B squared. So for example, if your vector is -7.66, -6.43, then the magnitude of that is we'll square negative 7.66. We'll square negative 6.43. We'll add those together and take the square root. And you get a length of this vector of 10. And by the way, if you're looking for something to hang this on in your brain to understand why this is, it's really just the Pythagorean theorem. So it's just the Pythagorean theorem. And remember, that says that if you have a right triangle, and this is A, and this is B, then the hypotenuse is A squared plus B squared square root. Well, vectors work that same way, where A would be like the x component, B would be the y component, and the length of the vector itself is the hypotenuse. Okay, anybody have any questions about that? I'll give you some problems like this to work on before Monday. Okay, have a good weekend.